about what the differences between these things, including maybe statisticians. And so I think there's some subtleties here, and a lot of times people just say, here's the definition of frequencies, and here's the definition of base units, without a lot of discussion about why they're actually different. And then they end up looking very similar, and they create a lot of confusion. I can see this when I work with scientists. They're very unclear what the difference is. And the problem here isn't the one or the other way of thinking, but the important thing is to understand the difference. Okay? So everything we've been talking about this class so far is what's called frequentist or classical index, where probability is interpreted as long-run frequencies. When we say it's a 95% confidence interval, we mean if you went through the rest of your life using this procedure, you would track the true value 95% of the time. It's a statement about the procedure. It's long-run frequency. The data are always viewed as random, but the data is some fixed unknown parameter. There's no frequencies involved with an unknown parameter data. It's a fixed number. It's not wobbling around. Okay? Bayesian inference takes a different point of view, which I know you did some of this in 701 and 705. Probability is interpreted differently. It's got nothing to do with frequencies. It's about degrees of belief. The probability that Oswald killed Kennedy by himself is 0.9. There's no random frequencies, no fluctuating frequencies in that way. That's supposed to be your personal subjective degree of belief about something. And often interpreted in terms of betting rates. What would you bet? There's nothing about frequencies there. And once you observe the data and Bayesian inference, you consider it fixed, and to you, theta now is random. Well, how can it be random? It's not fluctuating. Well, because we're interpreting probability as degree of belief. You can have a degree of belief about a fixed, non-fluctuating parameter. That's the appeal of Bayesian inference, is to make probability statements about parameters, as opposed to procedures like the confidence interval. The price you pay is you're going to give up the leftist column. You're not going to get frequency guarantees. I like to think of it as a little bit like, in quantum mechanics, is the Heisenberg uncertainty principle. If you measure the position of a particle, you give up any information about the momentum. If you measure the momentum, you give up learning about the position. You can either have an analysis of your beliefs about the parameter and give up with having frequency guarantees, or you can have something that gives you frequency guarantees, but it's not going to represent anybody's beliefs. There's nothing wrong with that. They're just two different things. The problem is the confusion. People do this, and they start to think of it like this, or conversely. So the point here is to keep the distinction clear. And what I want to do today is show you examples where they're different. Because part of the problem, I think, is in a lot of classes, you're taught this, but nobody shows you an example where they're different. You end up seeing in every example they're almost the same, which is really confusing. So I'm going to show you examples today where they're starkly different, where the Bayesian frequency bands are completely different. Now, which one's right and which one's wrong? Well, it depends on how you want to think about statistics and machine learning and learning. I just want to point out to you that they're different. Okay? And another confusing point is the word Bayes appears in so many places. So we're talking about inference, which is like learning theory, if you want to think of it that way. Bayesian inference is a type of learning theory, or a type of statistical inference. It's got nothing to do with Bayes theory. Yes, it's true when you do Bayesian inference, you use Bayes theorem. But using Bayes theorem is neither necessary nor sufficient for doing Bayesian inference. There's lots of frequentist procedures that use Bayes theorem. What makes it frequentist is the goal, that you want to have a procedure with certain frequency guarantees. If it happens to use Bayes theorem along the way, so be it. Conversely, there are forms of Bayesian inference that never use Bayes theorem. So don't confuse Bayes theorem, which is an uncontroversial theorem in probability, which does happen to get used a lot in Bayesian inference, but that's not Bayesian inference. So if you ever read the book by, what's that dude's name? Nate Silver? What is it? Nate Silver, thank you. He completely confuses the two throughout his whole book. It's a nice book, except for the point that he's completely confused about Bayesian inference. And it's the same with, there's this woman who has a really nice book about the history of Bayes theorem, and I've forgotten her name, so it's a very nice book. But again, the whole book has this massive confusion between Bayes theorem and Bayes theorem. It's the same with the Bayes rule in classification, right? That's the optimal classifier. It's nothing to do with Bayes theorem. You can call it the Finagle rule or something like that. It should have a different name because it doesn't have to do with Bayes theorem. Bayes net mechanics. Those are just directed graphs with probability distributions. They have nothing to do with Bayesian. You can analyze a Bayesian net using Bayesian or frequency. So unfortunately, if I had to go back, I'd eliminate these, right? There's something called empirical Bayes. It really has nothing to do with Bayesian. So beware that the word Bayes shows up. It doesn't mean you're necessarily doing Bayesian. And just to remind you of the basic mechanics of Bayes, and we can go into the mechanics in great detail later if we need to redo that. But I really want to emphasize the examples today. But remember how it works is we do use Bayes' theorem typically to get what's called a posterior distribution for theta given the data. You can't do this in frequency difference because there's no probability distribution for theta in a frequency world. It's a fixed constant. But in the degree of belief world, we can have degree of belief of theta given x. And by Bayes' theorem, that's proportional to the distribution of x given theta times your prior distribution for theta. So one of the things about Bayesian inference is you have to put a prior distribution to get things started. But again, some people conflate that with Bayesian inference. They think Bayesian inference is all about prior information. No, you can include prior information in frequency inference too. So Bayesian inference is not about whether or not you include prior information. It's about the goal. It's about whether your goal is to get degrees of belief or to get procedures with frequency functions. Anyway, you take the prior times the distribution for x, which is just the likelihood. So the prior times the likelihood gives you your posterior distribution, your posterior beliefs. And now you can do everything you want from the posterior. If you want a point estimate, you could take, for example, the mean of that. That would be instead of the MLE. Instead of a confidence interval, you could just find a set C whose posterior probability content is, say, 95%. That would be like a Bayesian confidence interval. Now here's where we get to the tricky difference. The interpretation of that interval is that theta viewed as random, my degree of belief probability that theta is C given the data is 95%. That does not mean that the frequency coverage, which is written here, is 95%. It doesn't mean if we repeated the experiment, you would contain the truth 95% of the time. And Bayesians are sometimes sensitive about this, but they shouldn't be, because the fathers of Bayesian inference knew this, and they said there's no reason why those two things should be equal. And the examples I'm going to show you are where these are starkly different. Okay? And part of the problem is notation. If we had agreed 100 years ago that degree of belief probabilities we use a V for, or something like that, and frequency probabilities of P or something, then fine, B of theta is 95%, but P of theta is not. Wouldn't seem somehow as bothersome, but we use the same symbol P for probability, whether it's a degree of belief probability or a frequency probability. Maybe that adds to the confusion. Okay, so what my goal is now is to go through some of these examples. None of them are hard, but I want to go through them slowly because although they're mathematically simple, conceptually it's very easy to get tripped up. So I want to go through them kind of slowly. But before I do, so the goal today is to compare really frequency coverage and posterior probability and just show you examples where they are really different. There are examples where they're almost the same, which is fine. But I want you to be aware there are examples where they're very different. So before we jump into it, any questions? Yes?
Why do you say that X is fixed in Bayesian? Like what?
Well, because suppose I want to estimate the mean blood pressure of the United States. That's theta. It's not a variable, it's not a random variable, there's nothing random varying, it's just a fixed unknown number.
Right.
Whereas the data, your individuals, like as I sample you, I'm getting different X's every time, they're all over the place.
Right.
So the random variables are random, that's why they call random variables, and that's why we were careful to call parameters, not random variables. It's a fixed unknown constant, it's not changing.
So my question was about under Bayesian, like you've of course said X is fixed.
Oh, well usually when you do inference, you've observed X already, so you're doing inference for theta conditional on actually treated as fixed. Yeah, so before you see it, it is random. Then it becomes fixed. Yeah?
Is it true that in a frequency setting you can't really ever say anything about theta? You can only say, I've got an expression. You can never say anything about theta before or after.
That's right. We're not making any degree of belief statement about it, but what I can tell you, it's a little bit like saying this. I'm going to set a bunch of traps for bears, and I tell you 95% of these traps will catch bears. Now, I don't know whether it's going to be this trap or that trap, but you feel some confidence using that trap because it has a high success rate, right? So it's exactly the same thing. You're right, when I get a confidence interval, I'll never know whether this is the one that contained truth or this is the 1 in 20 that didn't. At least I have the knowledge that, that this is a very reliable track that I'm using. That's right, that's the difference between the two. That's what you're giving up. In each one, you're kind of giving up something. All right, so I want to jump all the way to the end of the chapter. If you go to page 345, you'll see a picture that looks like this. This is one of my favorite statistics examples. It's called An Adventure in Flatland. And the example is due to Mervyn Stone, who's an emeritus professor at the University College London. And I used to have a blog, and I blogged about this example, and I was kind of shocked to find out how many people have never heard of this. I thought every statistician knew this example. Maybe in machine learning not so much, but certainly in statistics, and I was shocked to discover people my own age who never heard of it, and who actually had trouble understanding it. So I realized maybe it's more subtle than people think. Stone, by the way, is a great statistician. He did amazing work in the 70s, especially about this topic, about the relationship between Bayesian inference and frequentist inference. So if you want a little historical thing, go back and look at his papers. They're kind of very mathematical. They're not easy. There's a lot of group theory, but they're really important papers. But I can describe the example very simply. Okay. And what we're going to see is an example of where the Bayesian is going to have a probability of something, and the frequentist is going to have a probability. They're going to be very different, and we're going to try to understand what that means. So here's the thing. We have this big city that goes on, I've only driven a part of it. These are buildings. Okay. And I start wandering around kind of randomly in this city, and I drag a string behind me. So I drew a path there. Let's suppose, I go here, here. If I go backwards, the string, it's an elastic string. So if I were to step backwards, it disappears. It sort of shrinks back. So if I take a step backwards, you don't see that. But eventually, I'm going to end up somewhere. Let's suppose here. Okay, and now what I do, okay, so imagine I've done this. And by the way, this is one of these things like the Monty Hall paradox, where you might want to go away and simulate this on a computer later on. It's very easy to simulate because you might find it that doesn't seem quite right, but when you simulate it, you'll see it's true. I drop a treasure right there, and I bury it. Now, I flip a four-sided die, and I take one last step. So I either go north, west, east, or south. So, with equal probability. And so let's suppose, just for the sake of argument, I go north, okay? So suppose I go here. Okay, you didn't witness any of this. Now you show up and you see a string and you see me standing there, and you know the rule of how I did this. And your goal is, can you find the treasure? All right? But there's two of you. There's a Bayesian and a frequentist. Actually, I called them Bob and Carla, so Bayesian and classical. Should have Bob and Francine here. Anyway, the Bayesian and the classical. All right. So let's think about making inference for theta. Let's call theta, that's our unknown parameter, is the unknown location of the treasure. Now, you know I put it here, but really you don't know that. All you know is I'm here. So let's first of all notice when you see this situation, there's only 4 places theta can be. Remember, I only took one step at the end. So you know either I was here and took a step down, or I was here and took a step here, I was here and took a step here, here and took a step here. So actually, theta can only take 4 values, which is west, east, north, and south. Okay. Now the first step, so let's think through Bob the Bayesian. Bob the Bayesian says, well, I should put down a prior and a likelihood and multiply it. The prior is going to be what? Prior of all possible locations in the city. So that could be a complicated prior. Let's do the likelihood first. What's the likelihood here? And let's be really careful about this. So here's theta is west, east, north, south. the data are basically what you see there, what you see. And I want to ask, remember how we do likelihood? We always ask, if theta were equal to this, what would be the probability of what I observe? If theta were equal to this, what would be the probability of what I observe? So let's do it. Suppose theta was less. Suppose this was the treasure. And then, if this had been where I was, I know I could have gone here, 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 or here. So the observed data point has what probability? A quarter, right? So this is a fourth. How about if theta had been east? So if this had been where I was a moment ago, I could have gone here, 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 with equal probability. The observed data therefore has probability a quarter. And I think you can see now that for each direction, the likelihood function, this is not the posterior, this is the likelihood function, is a quarter, quarter, quarter. It's equal in all four directions. That already confuses a lot of people. But I hope that's clear when you see it just written out like that. All right, now we need a prior. Well, let's take a flat prior. Now, that's a little bit cheating because if I let this board go on for infinity, that wouldn't integrate to 1. But that's okay. Let's just imagine it's a very flat, smooth prior, and to a good approximation, it's not going to matter. We can just take it to be flat. We'll talk about what happens if you use other priors in a few minutes. For now, I just want to use a very smooth, flat prior. In that case, the posterior times the prior is basically flat, so the posterior is the likelihood. And so this is our posterior distribution. We now have a posterior distribution that puts mass a quarter here, here, and here, and here. All right, so Bob says, all right, I have a posterior distribution. That's my degree of belief that the treasure is in one of those 4 locations. So Bob says, all right, here's my guess of where the treasure is. In fact, we're going to be really generous to Bob. He gets to pick 3 locations. He's going to pick this, this, and this. We're really giving him an easy time. He doesn't even have to pick 1 location. He gets to pick 3 locations. So B, this set. So if I call that set B, what we see is that the probability that Bob believes, so the probability that Bob has, that theta is in B given the data, is 3/4, right? Just quarter plus quarter plus quarter. That's his degree of belief that the treasure is in those 3 places. Very simple calculation. Likelihood times prior. Now, let's think about Carla, the classical statistician. She says, you can have your posterior, Bob. I'm going to do something much simpler. I'm going to pick this set. The one that shortens the string. I'm just going to pick that singleton. She only needs 1. And she's claiming that her coverage, that is a confidence interval, treating A as random. Is it a random procedure? Yes, it is, because we see the data, and I take the one position that shortens the string. That's my confidence set. Depends on the data. And Carla claims that no matter what the true value of theta is, the probability that this traps the treasure, so remember that A is random for Carla, is 3/4. Notice that Bob would say, are you crazy? He says, my belief that theta is 1/4. Notice that how strikingly different those things are. Let's think if Carla's right. I want to claim, what does it mean to say I have coverage 3/4? I claim that no matter what theta is, that's the key thing in frequency space. It holds uniformly over theta. Whatever the true value of the theta is, wherever the treasure is, Carla's strategy will recover the treasure 3 out of 4 times. So let's think about it. When I'm at that, just before I took my last step, I had 4 choices. Which ones will Carla's strategy work for? She's always going to shorten the string. If I went here, here, or here, her shorten the string strategy would win. It's only 1 out of 4 that it would fail. So thinking of the procedure as random, the procedure is, my confidence set is the point obtained by shortening the string by 1. We get that the frequency probability that A traps theta is indeed 3/4. And if you don't believe this, here's what I invite you to do. You and your friends sit down, one of you is Bob, one of you is Carla, and actually you can program this and pretend you're playing this game, and you will see, it doesn't matter. And by the way, how are we deciding where to, how long to put the string? It doesn't matter. Make up any procedure you want. One sec. You will see when you play over and over and over again, if you are Carla, you will win the treasure 3 out of 4 times. And if you are Bob, you will only win 1 out of 4 times. There's no paradox, though, because there's nothing that says your belief in 3/4 means that you'll be right 3/4 of the time. That's the difference between belief and frequency. Question?
So we would have done the same thing with Bob as well. Bob could have shortened the string and put a Bayesian prior and did all those things.
Now, well, Bob puts down a prior, multiplies by the likelihood, includes the posterior. That's how you do Bayesian inference, right?
But like Bob could have followed the same procedure. He could have said that I
Yes, and
shortened
he'll
the string.
conclude, we just did it. Bob's posterior probability that shortening the string contains a treasure is 1/4. He believes only 1/4 of that.
Like it seems as if Bob is following a different procedure and Carla is following a different procedure.
Well, they are. One of them is doing Bayesian inference, one of them is doing frequency. And I'm just showing you that one of them is stating his beliefs and updating them with Bayes' theorem, and he's stating his posterior beliefs. And all I'm showing you is that has nothing to do with the frequency with which you trap the two values. They're completely unrelated quantities. There's nothing wrong with it. It's a correct statement of his beliefs. I told you I was going to blow your mind.
Yeah. But isn't that have to do with Bob picking a bad prior?
Well, I want to come back to the prior issue in a minute. This will hold, of course, for a sufficiently smooth prior. Yeah.
If Bob divided up into 2 cases, say, what's the probability, given that the last step was a retracing, a backward step, what's the probability, given that the last step was a forward step, and then estimate, what's the probability that that last step was a forward step, which would be 75%.
The problem with that is that's an ancillary statistic. So if I look at the data itself and this extra statistic lengthening or not lengthening, one of them is a subset of the other one. And so the posterior is unaffected by whether the posterior is completely invariant whether to the positioning of the string. This is something called the irrelevance of the stopping rule, which we'll talk about in another example. If you are going to follow Bayes' rule, you will not be able to use the ancillary knowledge of this string.
Okay,
That's a deep fact about Bayesian inference. There's things called ancillaries, which are statistics whose distribution doesn't depend on the unknown parameter. So, for example, the shortening of the string always happens with probabilities of quarters independent of theta. And it's a fact that the posterior never depends on any ancillary. When we talk about something called sampling to a foregone conclusion, that will be even more striking fact. All right. Any other examples? You're probably going to want to think about this some more. But I want to, again, emphasize that they really are different things. But now, can I save the day by choosing a different prior? Well, yes and no. For one thing, if I pick a proper prior, which is how in some sense I should do it, there will always be places in the parameter space where you do well, but there will be even more places where you do poorly. So you might recover some thetas, but you'll never uniformly do well over the whole space. I'm not going to prove that here. But there's no way to pick the prior that's proper, that sums up to 1, that will guarantee you that you'll do as well as Carla. What if I continue to allow improper priors that don't sum up to 1, but use a different one than I used here? Then it turns out you can construct a very particular prior that's improper, but that actually forces the posterior to behave more like Carla's procedure. However, once you start doing that, once you start carefully crafting the prior just to copy the frequentist answer, you have to ask yourself, are you even doing Bayes and inference? Right? Presumably, if you're choosing a prior just to copy the frequentist, there's no point in doing Bayes and inference. Right? So choosing the different prior here isn't really going to help you much. Yeah.
But we're going to sort of combine the benefits of both. You'd be able to actually say things about data, not just about your procedure.
But does it really represent your beliefs anymore? If you're just choosing the prior to get your frequency behavior, the whole point of Bayes and inference is you're supposed to be trying to represent your beliefs. And if you're only choosing the prior to chase the frequentist around, haven't you given up the game in some sense? It seems like you've admitted defeat, basically. Okay? And again, let me say that the great fathers of Bayesian inference, so this is Bruno De Finetti and Lenny Savage, they would say you shouldn't be doing that. They say you should just state your beliefs, repeat the posterior, and live with it. And that's it. And the fact that it doesn't have good frequency behavior, they would say, so what? You said, no one said it should. They would say that's not what statistics and learning is about. But I don't want to harp on it too long, because we have a few examples to go through, because I really want you to think through it. There's a mathematical kind of explanation at the bottom of page 247 you might want to look through. And I also put a second version of this example right after this. It's equivalent, but it's expressed differently. Some people find the second version easier to think of. It's about putting down strings like A inverse B, A, B inverse A, where you have two strings. This is called the free group with two generators, where you have two symbols and their inverses. And you start canceling out things. And you can rewrite the whole thing that way. I put it there in case this one's confusing. You let some people find the other one easier to pick up with their code. And again, if you're really excited about this, go back to Stone's original papers. In fact, I'm going to read you a quote. And what he writes in his paper is interesting because it's very mathematical. And then he gets to this. He says, it's clear that when Bob and Carlo repeatedly engage in this treasure hunt, Bob will find that his posterior probability assignment becomes increasingly discrepant with his proportion of wins, and that Carla is somehow doing better than she ought to. There is no message that will allow Bob to escape from his Promethean situation. He cannot learn from his experience because each hunt is independent of the other. So let me point out that when you play this game over and over with your friends, you should do a different game each time. A common misconception of frequent statistics is people will say, a 95% confidence interval means if I repeated it over and over, it would contain the true value 95% of the time. And then people say, yeah, but you don't get to repeat the experiment over and over. That's not the interpretation of the confidence. You should imagine yourself doing a different experiment every day with different values of the true parameter. And you will still contain the truth 95% of the time. That's because confidence intervals are defined in terms of the inf over all theta. It's uniformly. So in other words, you get a third friend to put the treasure down by some bizarre rule that they can change every day. Then you play the game. Then tomorrow you play an independent game. And you get a different friend to make up a different rule for putting the treasure, and you still play it. And in this sequence of games, independent games, you will still see that Carlo wins 3/4 of the time. That's what his quote means. All right, so you're going to want to go away and think about this. I want to do some more. So if we go, let's go back 2 pages. This is a more prosaic example, not quite as striking, but perhaps more practically relevant. This is the many normal means problem, which turns out to come up a lot in statistics. And a lot of problems you already know can actually be converted into this problem. Like function estimation, it turns out, can be converted into a problem like this, where you have a normal. Xi is normal with mean mu I variance 1. I equals 1 to n. So n normals, but each has different means. So let's let mu be the vector. All right, so this looks pretty straightforward so far. Now suppose the quantity I want to estimate here is not necessarily the mu's, but the sum of the mu squared. How far is this from the origin? And let's try to construct some sort of 1 two-sided confidence. So we usually use two-sided intervals. It'll just be easier to use a one-sided confidence interval. Now, I'm not going to do the frequentist calculation, but it's actually quite easy. So you can actually find a constant little cn that depends on the x's, such that this interval will track theta 95% of the time, no matter what the value of mu1, mu2, mu is. Again, you can do this as a game and do it over and over again with different values of mu every time. How do you do that? Well, just think about starting with the statistic, something like this. Does anybody remember what is the distribution of this statistic? Almost chi-squared. If the mu's were 0, it'd be chi-squared. If non-central chi-squared, maybe you didn't learn that one, but if they were mean 0, they'd be chi-squared. If the means are non-zero, it has non-central chi-squared. So from the properties of a non-central chi-squared, you can figure out now from here how to choose this constant to get a 95% confidence interval. So that's, I'm not going to do the calculation, but that's not too hard. But let's do the Bayesian analysis. So again, I'm going to use the flat pie because the calculations are always easier. Although that's, again, not crucial here. Well, actually, the choice of, I take that back. The choice of prior is crucial here. But if we're in the land of using fairly flat, smooth priors, taking it to the uniform doesn't change much. So the calculation now is what? The prior times the likelihood. What is the likelihood? The likelihood is proportional to n to the 1/2. So if we stare at this now, that's the posterior. If we just stare at this, and remember, from the Bayesian point of view, we're going to think of x as fixed and mu as random, well, it's still normal. We see that the posterior distribution for mu, given x, is a multivariate normal centered at x with identity covariance matrix. So now we want to think we have to keep our mind in the Bayesian world here that x is fixed and mu is random, and it has a multivariate normal distribution. So again, because x has a multivariate normal distribution, the posterior for theta squared is easy to compute. It's going to be also a non-central chi-squared distribution. So I don't want to encumber you with the calculation details, but we can easily find Cn. Maybe we'll put this on the homework actually. Yeah, this will be a good homework question. Don't worry, it's not hard. But you will find in the homework a Cn the following property then, that the probability that theta is in Cn given x over xn is 95%. Okay, so this is your posterior belief that theta is in this interval is 95%. And now we can ask again from the frequency point of view, from Harley's point of view, if we did this as a game and did it over and over again, how often would this Bayesian 95% interval trap the true value? And what Charles Stein proved in 1959 was that it's 0. More precisely, he showed that the probability that theta is trapped in here goes to 0 as n goes to infinity. So for large n, it's essentially 0. So again, it's just an example, and it's not saying one is right or wrong. It's an example where they're different. I just want to make them strikingly different. Now, in this case, there are ways to kind of fix things up. If you put a normal prior on mu, you're going to, instead of a flat prior, you're going to do a bit better, but you still won't get coverage 95% everywhere, but you'll at least get coverage 95% for parts of the parameter space. So that one maybe is less, that one doesn't bother people as much, although the difference between the probabilities is bigger than in the last example.
So here we sample, so say we assume a prior and we sample the parameter from that prior. And let's say that's how we repeat this experiment. How would the frequency interval perform, like when you actually sample theta from the prior?
Okay, so that's a good question. Suppose part of the game is now we have a prior pi, and mu is actually drawn randomly from that prior. So, of course, first of all, if we knew that, we would consider this to be part of the frequency properties, and we could include that information, right? So in that case, the Bayesian and the frequencies would agree. However, we could continue. What would happen if we ignored it and continued to use the frequency answer? It would still have coverage 95%, because the coverage is valid by definition for all things. So it doesn't matter whether it's drawn randomly or drawn or fixed or drawn even by adversarially. Coverage is 95% for every theta, so therefore it's true even if it's drawn randomly. Now, if you actually had mu drawn from a frequency distribution, and if you knew this, everybody would agree, there's no controversy in that case. The difficult case, of course, is typically mu is just some fixed unknown constant, or even if it was drawn from a distribution, we don't know what the distribution is. All right. Yeah.
So what does your belief really mean in this case? It seems like it's wrong.
Well, so the subjective point of view, though, is that everybody has their own beliefs, and I'll put on my Bayesian hat and say it doesn't make sense to say your beliefs are wrong. Your beliefs are your beliefs. That's the Bayesian point of view, right? Is that it's as long as you coherently state and manipulate your beliefs, being internally coherent. The fact that they don't happen to agree with frequencies is you should shrug your shoulders. I'm not necessarily advocating that. I'm just saying that would be the response. Okay, so let's keep going. Now I want to do one that's these have all been kind of fun, but now I want to do one that's actually quite important and practically relevant. This is called sampling to a foregone conclusion, and it was first raised by, I'm going to say Cochran, and it came up because of sequential clinical trials. So in a clinical trial, the ideal thing is when people want to say some medication is working, you do a clinical trial, a drug company does a clinical trial, and they'll take a bunch of people, randomly assign someone, say, the treatment, someone to a placebo, compare them, whatever, or two different treatments, whatever. But sometimes clinical trials, you can't do them that way. What you need to do is do them in a more real-time basis. A person comes in, maybe you randomly assign them, say, to treatment or control, and you treat them. Then another patient comes in, and you treat them. And so it's done sequentially. A lot of clinical trials are done this way, as a sequential trial. And now you face an interesting problem when you do sequential trials. When do you stop? How do you know when to stop a clinical trial? So there's a large literature about this. So let's simplify things a bit and say we've got these data points that are coming. Let's make it just normal theta 1. You can think of this as sort of, maybe each person comes in and I give them treatment and control and give the difference or something like that. So that's what xi is how well you do on treatment versus control or something. And so theta 0 would mean no difference between the drug and the placebo, and you're interested in knowing whether theta is different than 0 or not. All right. So now let's pretend you're an unscrupulous drug company. Actually, I hate demonizing drug companies. It's so cliche. But I'll do it for the sake of the example. So you're now the guy that hired in the drug company where they do hire a lot of people, statistics and things like that. And you're designing this clinical trial. And you say, here's what I'm going to do. I'm going to stop. I'm going to keep sampling until Rugan is bigger than, let's say, 10. Okay, so let's just pretend we recruit a new person every day. So every day we do this, we keep data, we keep collecting data, X bar is going to change. And as soon as we hit 10, I stop. So let's think about what this means. Think about if you were doing a hypothesis test to test whether this theta was 0 or not, you would probably use something like, the z-test you learned, something like that, which is exactly this, right? So you probably learned, well, this was significant if it was bigger than 1.96 or 2 or something like that. So that's why I picked 10. It's going to look highly significant. We're going to stop when the testing just looks highly significant. But wait a second, let's look at it from Bob's point of view. He's going to take the prior and multiply by the likelihood. And so what we're saying, by the way, is that we're stopping when X bar is about 10 standard errors away from 0. So what does the likelihood look like? The likelihood, remember, is what's the width of the likelihood? About 1 over root n. And we're over here at 10. So the likelihood looks like this. And now we're going to multiply it by some prior. Pick any prior you want. Some smooth prior. Asymptotically, that's not going to matter much anyway. But now you wonder, well, wait a second, do I take into account the fact that this guy stopped precisely because the likelihood is so far from 0? And now here's a little calculation you can do. This relates to the question you asked earlier, which is you can prove, this is called the irrelevance of the stopping rule. The posterior is unaffected by the stopping rule. That is, suppose that this happened on day 328. The posterior you would calculate on day 328 would be the same whether you stop because you decided ahead of time I'm going to stop on day 328, or because I used this weird stopping. That might seem a bit odd, but if you just work through Bayes' theorem, you'll see that the stopping rule falls out. It's called the irrelevance of the stopping rule. So the posterior is not affected by why you stopped. In fact, in the Bayesian world, this is considered an advantage because trying to account for the stopping rule turns out to be, particularly in this, can be a difficult calculation. In particular, here you have to account for the fact that you never get anything likely to be 0. You have to adjust the confidence intervals to account. And in this game I just made up, it's pretty easy. But when you have more complicated stopping rules in real life, it's often very complicated to make sure that your confidence intervals still have the correct coverage. From the Bayesian point of view, because of the irrelevance of the stopping rule, instead of being a bug, it's considered a feature. It's like, it doesn't matter, it's a feature. And the posterior will look like this here. Okay, now let's suppose for the moment that the drug is bogus. It doesn't do anything. It's equivalent to the placebo. So the true value is 0. So let's just picture this. I've got a drug that doesn't do anything. It's equivalent to the placebo. Everybody comes in. I give them the drug and the placebo. I take the difference. I'm just getting normals from normal 0 1. I run this until it looks like this, where 10 standard errors from 0. Now the first question you might ask is, how do I know this will ever happen? If the true value is 0, will I ever get a likelihood that's 10 standard errors? Maybe this will never happen, right? Maybe it will always hover around 0. Well, it turns out, using something that you probably did cover sometimes, called the law of the iterated logarithm. It's something, usually in 705, you teach the law of large numbers, the central limit theorem. There's a few other cool probability things that don't get taught because they don't get used as much. This one's called the law of the iterated logarithm. Anyway, using the law of the iterated logarithm, you can show this will happen with probability 1. Even though the truth is 0, you get these occasional large fluctuations with probability 1. So this, if you were to simulate this in the computer, you don't have to worry about the computer running forever. It'll stop. Okay. Even though the truth is 0. But now we can see that when you compute your 95% posterior region, it's going to be over here. And when we compute the coverage of that, the frequency coverage, if we ask how often does this contain the true value, from the frequentist point of view, remember you have to say what's the coverage at every possible true value. Well, what's the coverage of this interval when the truth is 0? 0. So this has frequentist coverage 0. That is, the probability it'll trap the truth when theta is 0 is 0. In particular, the probability that theta is trapped in the Bayesian interval will be 0. The frequentist interval will adjust for this fact because by design you construct frequentist intervals so that this is equal to 95%. And it's going to involve enlarging this interval and so on. But the Bayesian interval, again, the 95% Bayesian interval will have frequentist coverage 0. This one is less playful than the last example. The other examples, I think, are kind of intellectually fun and very revealing. But they don't really come up so much in practice. Nobody's looking for treasures in flatland that I know of. But this is actually a real problem. And it's actually something that's debated quite a bit, which is what should we do in sequential clinical trials? And my understanding, and some of the correct me wrong, is I think the FDA standard is still to use frequentist methods to analyze sequential trials. There are people lobbying the FDA, though, to use Bayesian methods. And I think they may have been used in a couple of trials. I'm not 100% sure. But what makes that example interesting then is it shows you this is a case where it matters. This is a case where if you would pop open that description your doctor gave you, you might want to wonder what rule the FDA used to analyze data.
Wouldn't it be like you said n will be finite, but it could be like a trillion.
It's true. N could be very large, especially if I big K 10. It could be very large. It could take a long time for this to happen. That's true. But if you pick, say, I don't know, 2 or 3, it might not, I haven't done the calculation, but it may not take quite as long. Yeah, so that's interesting. Once we compute, but I don't know what the full sample size. All right. Everybody still okay? Yes?
Since you're multiplying by the square root of n, wouldn't the sample mean be very, very small at the time the confidence interval excludes 0? So it wouldn't include 0, but it would be very, very close to 0.
It'll be very, very close to 0, but I'm drawing this on relative to the concentration of the likelihood. So remember, when you say x bar is close to 0, we usually mean in terms of how many standard errors is it to 0.
Right.
So I'm trying to get across that, yes, you're right, of course it's going to be over here, but the posterior is going to be even more concentrated.
I agree that if you're the FDA, you're saying, well, this term doesn't make no difference, but it makes almost no difference.
That's a good point, actually. So, yeah, so if we stop when x bar, let's think. So, yeah, so that's actually a good point. So it might be that it's significant, but has a small effect. Yeah, that's actually a very good point. And in fact, that gets to a whole different controversy, which another confusing one, which is the difference between statistically significant and scientifically significant, which is a whole other thing we can talk about. But you're right, this wouldn't necessarily mean that your estimate of the data would be large. Okay. Next, got 1 or 2 more. Then I will do the theorem. Let me just repeat to you that I'm not trying to, maybe I'm trying to be balanced. But I don't want to, I want to really emphasize the difference between that. So I'm trying to prevent the murkiness between the two different words. Okay. Should we do, yeah, let's do GoDaddy as an example. example, I'm actually not sure who's the first person. I credit it here to V.P. Godambi, who was an Indian statistician who spent most of his career in Canada. But I think there were antecedents before that. I just couldn't remember who it was, so I just attributed it to the name. Here's his example. So suppose I have a bunch of pieces of paper. 1, 2, up to 10. So where this comes about, by the way, was Godambi was very interested in survey sampling. Survey sampling is obviously a very fruitful area for statistics. And he got to thinking about this, and he said, well, let's think about what we're doing when we're survey sampling. Think of each of these, I called them N pieces of paper. Raise bidder, say N people. And I want to measure something about the population, so what do? We take a sample from the population. To keep it simple, so I want to pretend everybody has an attribute, C1, C2. This could be any real number, but just to keep it simple, let's say it's binary. That's not necessary, it'll just make it simple. And, all right, and what I'm interested in is the sample average. And so in survey sampling, we choose some people randomly. I'm going to do it a little bit differently than we would normally sample, again, just to make the calculation simple, which is the following thing. I'm going to draw S1, S2 to Sn, where these are just independent Bernoullis. Did I get a probability? Pi. Pi is a known number. So, you don't want to measure everybody in the population. You usually just draw some random sample. This is a little bit different. I'm flipping, for every person, I'm flipping a coin and deciding whether to measure them or not. And with some probability, let's say, 0.01 or something like that. So if it's 0, I don't get to see this. If it's 1, then you get to see, you measure this thing. A more complicated and realistic example is oftentimes people come in and you do randomly decide whether to measure something, but it might be something expensive to measure. And so oftentimes this Bernoulli will actually depend on a high dimensional covariate. So for example, just to make up an example, I measure your gene expressions on 5,000 genes, and then I randomly decide whether to measure something that's pi could then be a function of something complicated. That's when this example actually gets really interesting. But to keep it simple, just a fun flip. All right. So we do this, right? And I'm going to get to see some of these guys, and I'm not going to get to see all of them. Let's first of all do the frequentist answer. The frequentist answer is called the Horowitz-Thompson estimator. It's kind of what you'd think it would be. It's just this. This is a standard estimator that's used in survey sampling. So let me show you what I'm doing. Is I have SCJ times, the reason why I'm multiplying by SJ is because if your SJ is a 0, I don't get to see it. So this is really just keeping track of the ones that I get to see. But then for each person, I'm dividing through by the probability that I got to see. And again, in a more complicated example, this might actually be a function of J and other things, but I'm just doing the simple case. So this is very simple, and if you just take the mean of this, you'll see it's theta. And actually, it's easy to get a confidence interval because, remember Hoeffding's inequality from 705? If you use Hoeffding's inequality here, we'll review Hoeffding's inequality later in the course. But it gives you something like the probability that theta hat minus theta. In this case, you get something like this. So we have a precise bound on how far theta has from theta, and from that we can get a confidence interval. Okay, now let's try to do Bayesian analysis, and this is Fernandez says the following thing. This is somewhat controversial. Not everybody agrees with this. But this was his view. He said, well, we compute the posterior. Actually, we can compute first the posterior on the C's. But the problem is, what's random here? What are the data? In some sense, randomness is coming from the S's. That's our random variables. And now we have a bit of a problem because if we put down what that is, that's Bernoulli. So that's pi to the sum of the S's, 1 minus pi. Right? There's no theta in there, or C's for that matter, except for the hard constraint that, of course, the C's you did see, if they didn't agree with, if you saw C1, and you now have, you know C1. But apart from that hard constraint over the rest of the C's and over theta, this doesn't involve the unknown parameters. The C's you didn't see and theta don't even appear in the likelihood. Thought of as a function of theta, this is likelihood is flat. The likelihood contains no information about it. And hence, the posterior is equal to your prior. And so no learning takes place. Kind of weird. Now, let's pause and think about that for a second. So this, when this first was brought up, this caused a bit of a stir. And there's a paper by a guy by the name, and I don't know if I'm gonna spell this right, but something like Erickson, where he shows that actually there may be a deeper way to analyze this which gets rid of this problem. Basically, he says, well, let's think of the C's as random variables. Let's pretend they're like a draw from the beginning of an infinite draw of random variables that were drawn from some other distribution with some other parameters in it. And so if you kind of start adding layers to the model, he's able to recover estimators actually that look like the Horowitz-Thompson estimator. Right?
This is kind of like the noiseless case, right? If you did the noisy version, would it not, would you not have C's in the, A's in the posterior?
I don't think it would help.
Because if I modeled like, when I draw,
Well, that's what I mean by, if you think of these as draws from a normal with some distribution.
yeah, right,
Oh, yes, that's the superpopulation
I see.
version. Right. So, for example, if I think of these C's as a draw from normal with mean theta, you can get a very similar answer out of it. The reply would be, but who says the C's are normally distributed? In fact, let me tell you, they're not. They're just some crazy set of numbers. Right? So this is why there was some controversy about this. So this one's less clear. I think there's, people take different sides of this, and whether this is a good example, but it's definitely worth thinking about. So now I want to tell you something a little bit more, can we say something a little bit more mathematical about this? And so enter into the fray David Friedman, who was a statistician at Berkeley, who wrote a very interesting paper in 1965. And I'm going to tell you what that paper says. A very interesting theory. So I'm at page 300, and I can't read the page number. What is that, 349 maybe? Section 12.7. Let me say that despite everything I've said right so far, I've picked examples right to make things look different. In your typical friendly parametric model, like a normal model, there really often isn't a lot of difference between the Bayes and the previous stuff. And so that's why people tend to get confused. So I purposely pick things that make them look different. However, there is one place where they always tend to be different. This is when anytime you get to a high dimensional problem or a non-parametric problem. That's when they tend to diverge. So Friedman said, let me take the simplest non-parametric problem in the world, and let's ask the following question. In a typical, very simple non-parametric problem, are the Bayes and frequentist things likely to agree? And here's how he did this. He said, look, let's suppose, so his goal was to try to make this more mathematical. He said, let's just suppose I have a sequence of random variables, IID, drawn from some unknown distribution. And let's suppose each xi takes values from the natural numbers. So it's non-parametric in the sense that the distribution P really has, an infinite number of parameters, namely the probability of x equals 1, x equals 2, x equals 3. To describe P, I would have to list, it's like a multinomial, but with infinitely many categories. So this is kind of the simplest non-parametric problem. All right. So the model, to keep it non-parametric, what are we going to assume about P? We're going to just assume it's a distribution. Script P is the set of all possible distributions over this sample space. All right. Now, let's do a Bayesian analysis, and we'll put a prior mu on the space of distributions. Now, some of you have done some non-parametric Bayes already, and some of you haven't. So we're going to have a lecture about non-parametric Bayes. For those of you who haven't done it before, let me just tell you that it might seem how hard to put a prior on the space of all distributions, but there's lots of examples actually. So we're going to construct lots of them next week. So we'll do the details probably on Monday. So mu is some prior distribution on the set of all distributions. All right, and now what we can do is, so imagine this blob, if you will, is the set of all distributions. I can't really draw the set of all distributions. Now we can imagine that here's the true P. I'm going to make it a dot. So there's some distribution P. Let's say I pick P. Now I draw an observation from P, that's x1. I draw a second one, a third one, and I give you this infinite stream of observations. Now try to picture this. So you have a prior over this space. And as you get more and more data, you get a posterior distribution. And you can imagine the posterior is going to change. And what you hope is that it would concentrate around the true distribution. We would say that it's consistent. So we've talked about estimators being consistent. You can also talk about posterior distribution. So it just means that the posterior concentrates around the true distribution. So I wrote that out here. Technically, it means that the limit of the posterior distribution, which I wrote like this, should be a point mass at the true distribution. We want that to happen where we want. That's what it means to be consistent. And this posterior is converging to a point mass at the true. So now you can draw a diagram that looks like this. And again, it's a very stylized diagram of what that is, which is for any pair. So here's the set of all distributions, and here's the set of all possible priors. And so a given pair will consist of a true distribution P, and somebody picks a prior. So the way to think about this is, again, maybe as a game. Nature picks a distribution P, statistician picks a prior on the set of distributions U, and now the game goes on. Nature generates data, statistician computes the posterior, and now we can ask for this particular pair, either it's going to be the case that it's going to be consistent, or it's not going to be. And what Friedman asked was, in this space, how many pairs are consistent? And the kind of surprising result is, I'm going to draw a picture of it. It sort of looks like this, a set of consistent pairs. Technically, what he proved was that the set of pairs that are consistent are what's called a first category set. So first category in topology is like a null set of measures. You know, in probability theory, that there's sets that have probability 0, like they're small sets. Like, you know, if I have a uniform distribution on the interval, and I pick some finite set of points, any finite set of points is probability 0, right? It's a null set. There's a topological equivalent that's called a set of first category. Sometimes it's called a meager set in some textbooks. It's the topological equivalent of a null set. It was a very small set. And the surprising result in Friedman's thing was that the set of pairs that are consistent is meager, or first category. Okay? And I want to find the quote about this. I left off the first one. So it's unclear. What's left is what's the interpretation of this. It doesn't mean that you can't find priors that give you consistent posteriors. They do exist. You can construct priors that will give you consistency assuming certain regularity conditions. It just means that they're very rare. It means that if somehow you're choosing a prior just to get a consistent posterior, and you're picking a very special prior, they're not common. And interestingly, he proved a corollary to this. He said, imagine if I have two basins with two different priors, how likely are they to merge as they get more and more data? And again, he showed that the set of pairs in which people's opinions merge is meager. It's the way I love this quote from this. He puts it, this is a very, very mathematical paper, and also he says, it is easy to prove that for essentially any pair of Bayesians, each thinks the other is crazy. It's not the usual way of stating a theorem, but that's how we kind of state it. Okay, so that's an interesting kind of first attempt, I think, that was to try to mathematicalize how common are disagreements between frequency Bayesian inference systems. Because since then, that's 40 years ago or 50 years ago, there's been a long sequence of papers going into much, much more detail about this. But I would have to say, I would summarize it all in the following way. 3 points. One, they are conceptually distinct. You should really just keep in mind they're different. Use whichever one you like, I don't care, but just keep in mind what you're doing. Just don't get confused. 2, the examples I showed you are pretty extreme. I think in typical low-dimensional parametric inference, Bayesian and frequency inference typically are very close together. However, the third point, which is more relevant for this, is once you get into high-dimensional statistics or non-parametric statistics, they completely disagree. And this is really relevant because, you know, it's in the last 5, 10 years, all of a sudden we're doing all these high-dimensional models, and people are kind of rediscovering all these old debates everybody used to have. For a while, it was like, look, every statistics conference, and you went to the bar after the talks, and everybody just argued about Bayesian versus ridiculous, and so on. And then after a while, people got much more practical, especially when certain algorithms came about where you could actually compute things, like Monte Carlo Markov chain methods, and people got into the business of just actually trying to solve problems and stop arguing and so on. But then I think it's kind of, I've seen a kind of revival of the debate again, because now we're doing all these really complex high-dimensional problems where they can look very different. So we're kind of in a state again, I think, where we're seeing a lot of revival of this kind of discussion. So that's the, yes?
So like in order for your, so say even if you consider a frequency confidence interval, for that to be consistent, you would need some condition like, you know, identifiability of your likelihood or whatever.
For in general this problem, or general?
I'm saying in general.
Well, in general, of course, to get a frequentist confidence interval with the right coverage, you require conditions, and you have to do, and it's on a problem-by-problem basis.
Right.
One of the nice things about Bayes is it has a certain universality to it. You take the likelihood, you multiply by the prior, you're done. That's how you solve every problem. That's kind of nice. It's like an algorithm. Frequentist inference is like every problem. Can I construct a confidence interval? Can I show its minimax? Can I show that it's a good confidence interval? So in some sense, it's harder in many ways. On the other hand, the guarantee you get out might be, more pleasing. So there's a trade-off.
under what conditions do you have a consistent posterior? Like, are they the same conditions as in?
So no, the conditions, so the plan then is on Monday I want to cover non-parametric phase. And what I want to do there is show you how non-parametric phase is done in density estimation regression. Then we'll talk about what are the conditions under which the posterior is consistent in the frequency space. And when is it minimax in the frequency space. So actually we'll talk about that on Monday. One thing I'm not sure about though is should I start with the review of like the basic mechanics for parametric phase difference. And again, I'm getting kind of, I've talked to your professors and stuff, no wonder I'm not getting a clear picture of how much you covered there. So if I said with a normal prior and a normal likelihood, find the posterior, is everybody comfortable with that? Is anybody, well, I can't say is anyone not comfortable, everybody's too embarrassed to put their hand up or not. But I'm not sure how to do the poll then. You know, or something like if I had a binomial with a beta prior and I compute the posterior, you know how to compute the posterior? How many think they could compute that posterior? Okay. So those basic manipulations for parametric models, then I'm assuming you're pretty comfortable with them. And so what I want to do on Monday now is get away from this foundational stuff. I think one lecture of it is kind of fun, but then it gets tiresome after a while. So we'll get back to how to do calculations, and we'll talk about non-parametric phase difference. And how do you construct priors on these big spaces? And how do we do the corresponding thing, like density estimation and regression, from the Bayesian point of view that we did already from the frequency study. So that'll be the topic on Monday's class. Any questions? Yeah.
Are there any frequencies larger than
What?
hierarchical models?
Yes, so hierarchical models are a good example of you can do it completely from a Bayesian point of view or completely from a frequency.
Now, how would you go about doing it?
It's called empirical Bayes, unfortunately, which is a bad name because it's purely frequency. Anyway, oh yes.
If you, especially an example of where data really is coming from a prior, the frequency doesn't know what the prior is, and so we will unfortunately
Yes, they would. If the average over required to. Would it be narrower? Probably.
What would be
It would be very problem specific. But they could still be different, but both have correct coverage. So listen, go away and think about the stuff. I mean, it might give you a headache, it might make you mad, it might make you happy, I don't know. But it's really interesting stuff to think about. It's just really good to make sure you know